Hello, good morning, and welcome to IMR's July webinar on advanced machine tool monitoring using machine data and low-cost sensors. In this webinar, we're going to explore how IMR and Dawnlough are deploying those low-cost sensors and controller data acquisition solutions to give unique insights into manufacturing processes. We're delighted to be joined this morning by Paul Moisy, a project engineer at Dawnlough. Paul is a mechanical engineer with experience in process design and implementation with the manufacturing sector. At Dawnlough, Paul works closely with the leadership team to target, plan, and manage strategic process and cultural change control within the organization. He's currently investigating contemporary process development and integration methodologies aimed at facilitating Industry 4.0 growth within the company. But first, I'm going to bring in IMR's Head of Machining Technologies, Chris Judge. Chris has extensive experience within the precision engineering sector, working with technologies from CNC machining and abrasive water jet cutting to EDM. He leads a number of programs that researches and implements new and emerging technologies to ensure companies always stay competitive in their market sector. And he's involved in EU funding research programs within the Irish precision engineering space. If you have any questions throughout the webinar for either Paul or Chris, you can use the question and answers function found on the bottom of your screen, and we'll get to them at the end of the webinar. But first up, welcome, Chris.
Thank you, Gary, and good morning, everyone. As Gary just mentioned, my name is Chris Judge. I am the Head of Machining Technologies at IMR, and I'm just going to give you a couple of slides just as a background on IMR for those who do not know who we are. It's Irish Manufacturing Research. And we currently have two sites, one based in Mullingar, where I am at the moment, where we have a lot of our lab space, our robotics, additive manufacturing and machining. And we have also office space in Dublin as well. And why we are set up, so IMR is main remit is to help Irish manufacturing companies to grow and to scale, to hire new people, hire new talent, upskill. We're not predominantly in the space of blue sky research, where you're thinking 5 to 10 years out. We're more interested in working with engineering companies adopt new and emerging technologies, making sure that Irish manufacturing companies are ready for the latest technologies that are coming around the corner and help them to understand and de-risk those technologies. So we currently have about 95, almost 100 staff now in IMR. And a key thing to note about the makeup of IMR is about 50% of our staff are from an industry background, including myself. I'm originally was a manufacturing manager in the company and worked in a precision engineering company for about 20 years before I joined IMR. And that allows IMR to align its research with tangible results for manufacturing companies and to make sure that we're helping companies affect their bottom line. And our key buzzwords are focusing on demystifying, de-risking, and delivering new and emerging technologies. And in order to do that, it's not necessarily about having the equipment and access to the equipment, however that is important. It also allows companies to understand what is required for them to onboard the technology. Is there an upskilling aspect needed? Is there a different skill set that's not readily available? And to that end, then IMR also supports training and delivering training on some of those new technologies. So for this morning, we're going to go through how the team at IMR worked with Dawnlough across the two projects to deploy low-cost sensors to monitor various aspects of the CNC machining process. And monitoring CNC machines is an ongoing challenge for companies, and depending on the level of data that companies want to get. And what we did in these projects was we looked at getting data at a fairly granular level to give some insight into the process, but seeing what could be done with relatively low cost sensors. So the first project that we had up was a project called DDMS, or Data Driven Machine Services, and involved in that project from an Irish point of view was IMR, Dawnlough and Key Plastics, and then it was done with another group of companies in Spain as well. And if we focus on just the Dawnlough aspect of the project, we had a challenge statement from Dawnlough around monitoring the current state of CNC cutting spindles. Now, CNC machine tools, for those not familiar, the machining spindle is a very, very finely balanced cutting spindle. They can run up to 20,000 RPM or more. They generally have ceramic bearings and are very easily damaged. but in that they're very expensive to repair and they can be very long lead time. So when they're in operation, it's very difficult to identify the health of that spindle. Is it going to last a week? If it has had a knock, is it damaged? Do I need to replace it now? There's a lot of questions to answer. And there's a lot of influencing factors that can cause that spindle to fail. You can have an imbalance in the spindle itself. You have thermal growth, you have operator errors, vibration through different things, or poor programming and machining strategy. So there's a lot of things that can occur that can be detrimental to the life of that spindle that companies are trying to understand and try to find ways to be able to monitor. And how can we visualize the current health of the spindle? If I stand in front of the machine at any given time, is that spindle functioning properly? Is there a problem with it? Should I consider replacing it or getting maintenance carried out on that spindle? So the solution from an IMR point of view was we engaged with our IoT team to look at the spindle and what we wanted to monitor on the spindle. And we looked at deploying different sensors around vibration, temperature, power and energy monitoring. And we settled on vibration as being an already recognized way of monitoring the health of the spindle on machine tools in the industry. And we looked at deploying that onto the machine tool. And then we brought in our data analytics team as well to trend the data that we were acquiring from the machine so we could visualize and understand what was going on within the process. So within IMR in our labs in Mullingar, we built and tested a system to acquire vibration data from the CNC machine spindle and then also controller data. And what we did, we were able to correlate this data set. The first thing we did was we visualized the data at an operator level. So at the screen beside the machine, we had the spindle vibration, we had the temperature, feed rate overrides, spindle loads, spindle temperature, part count. We were also able to very easily visualize OEE data because we were capturing the runtime of the machine. Once we had this data started to build up over a period, we handed it over to our data analytics team and they started to look for trends within the data. Now, this is where the industry expertise comes in for it, because our data analytics team looking at this in isolation would not identify what's going on or be able to paint a picture. So we looked at things like feed rate overrides. For us, that's important because if an operator is adjusting the feed rates overrides on the machine quite frequently, quite a lot, that could be affecting how the machine is performing and also put undue strains and pressures on the machine spindle. So are the operators changing and resetting these on a regular basis? Interestingly for Coolant, we discovered that they were not. So they're running their programs, their production programs consistently. However, we did identify certain trends, and this was taken over a 3 or 4 month period, and each blue dot you have there represents the highest spike of vibration for that day. And you can clearly see 2 anomalies here over a 3 month period. And because we were not only had vibration data, we also had a level of controller data, we were able to identify at what time, what date, what program, what tool number, what spindle load, and paint a picture of what happened in these incidents. And being able to do that, we identified in both cases that the machine was actually in a setup mode. So the machine was being set up, or the operators were manually setting up the machine or blocking up material. And this is when they were getting these spikes or anomalies, not when the machine was in a typical production scenario. And that it wasn't so much a witch hunt to go back to the operators, but just to inform operators. And all the way throughout the project, we informed the operators at an operator level that this is what we're seeing. These are things that are going on your machine, and this is how you can change that, or things that you need to watch out for. So the thing to move on from that, the question was then, well, we can see that there is bumps and things happening on the machine, which is not great, but how do we know if the spindle is still healthy? So we identified that if we run a warm-up program, a standard program each morning, and we get a vibration signature of that warm-up program, and we know what that looks like for a healthy spindle, we can effectively run that any day. And then we can do a comparison from the day before a bump or the day after a bump to see, is the machine spindle still the same, or is there excessive vibration caused? So the graph we have here is an image of a spindle running at 500 RPM, 1,000 RPM, 5,000 RPM, 10,000 RPM. So we know what a healthy spindle looks like, and we're able to run that at any point to identify if that graph remains the same. Now, subsequently, a knock-on from this project has been, well, if we can do that for a warm-up program, can I do that for a production part? Now I can get a vibration signature for what a healthy production part looks like. And if I can do that, if I come back in 6 months' time and I set my machine up again, I can compare the vibration signature from the setup in 6 months' time to what it was like when I ran it the first time, to ensure that, or see, is there differences between my original setup to this setup. Now you're getting into the area of batch-to-batch verification, which is very, very interesting in itself. Another knock-on consequence of this, or area of this, is where we're doing vibration monitoring for new programs. If you're in a program for the first time, you can graph and visibly see spikes within the machining process. You can actually give that information back to your CAD/CAM team and go, can you change the tool paths to remove those spikes? But because we have a high level of data, we can see whereabouts in the program, what was the tool number, what was going on at the time, and the CAD/CAM team can change the programs, then change tool paths to reduce these spikes, and that creates a more optimized program. And they can do that in the first time round instead of having a system of continuously feeding back from CAD/CAM to the production floor. On our second project, which is an ongoing project at the moment, this is an Enterprise Ireland funded project with Dawnlough, Coolant Precision and T&T Precision. It's been going on now for the last 18 months. It's almost coming to a close. And we look to monitor different aspects for each of the companies. For this, we're just going to concentrate on the Dawnlough challenge statement that they had. And what Dawnlough wanted to ask was, is it possible to monitor CNC coolant using inexpensive sensors? Now, you can monitor CNC coolant, and there are solutions out there, but they're very, very expensive and they're not commercially viable. To monitor one machine, we've seen prices in the range of 9,000 to 12,000 euros to monitor one machine. But is it possible to deploy low-cost sensors to monitor the coolant on a CNC machine? On a CNC machine, it's a very manual process at the moment. People are using pH sticks, refractometers, and controlling the coolant can optimize tool life. It is a health and safety concern for companies. There's a lot of areas why it's important. Even the coolant level is an important one. And the amount of times that an operator will go home at the end of his shift and forget to top up the coolant when he leaves the machine automatically running, to find out the next morning that the machine stopped running 30 minutes after he left because it ran out of coolant, just because he didn't top it up. Can we visualize that so people can see it very quickly so it doesn't happen? And the second aspect is around energy monitoring. And we did this across all three companies. Can we monitor the energy at the machine, not at a factory level, but at a machine level? And we wanted to do it at a machine level because we wanted to raise the awareness for the operator at the machine, because they're the main guys that can influence those numbers. And if we can raise if we can raise awareness around the cost of operating a machine at a machine level, that they're the areas that operators can influence. And this goes back to visualization of data and the data that you put in front of people. I'm a firm believer that you put a number in front of somebody that they can influence, it's a relevant number to them. Don't put a number in front of them that means nothing to them. And the solution in this case here, again, we had our IoT team identify suitable sensors. We created a dashboard at an operator level that's on the machine. We got our data analytics team involved in visualizing the data over a long period. And then we began to report. In this case, the second time around, we began to report in Power BI, because a lot of companies are using Power BI to build their own reporting systems. And we also found it very useful as well. If I look at the energy monitoring one here, and these numbers are not live data, they're for reference only. And we visualized the amount of energy that the machine was using across 3 shifts. And instead of visualizing the amount of energy cost that the machine is using when it's in production, we decided to visualize the amount of money the machine was, or energy the machine is consuming when it's not in production. If a machine is cutting parts and it is making parts, well, there's not much you can really do during that time. It's going to influence that cost. However, if the machine is idle, how much time over a period of time is it idle for, and how much is it costing for that machine to be idle? In other words, people just not turning off the machines, or moving the machine into a soft e-stop where they're turning off the hydraulic systems on the machine. So we were able to identify this and visualize this at a production level, at a machine level. When it came to coolant, we began to visualize different graphs. We looked at the pH correlated with the temperature, and we weren't sure what we were going to find when we started visualizing this level of data. But we did get some insights, and here's one, for example. The blue line represents the pH, which doesn't change, it's fairly consistent. However, anywhere you have a red area on the graph, this is the level of the coolant where the coolant goes below 50%. And what we observed was that when the coolant volume goes below 50%, we've seen a dramatic increase in the temperature of the coolant. Now, that of course makes sense, but you might not consider it being an impacting factor. But if the temperature of the coolant raises by 5 or 6 or 10 degrees, that will affect the overall performance and accuracy of the machine. Now you're getting variations in the operating temperature of the machine that is directly correlated to the volume of coolant in the tank. So if we maintain the coolant level, we will maintain the temperature of the machine much more easily. A second insight for one of the other companies we looked at was the environmental temperatures around the factory and the external temperatures. And this came on the back of how the challenge here was how much do I need to control the temperature within my factory to reduce the influence it has on the operation or the positional accuracy of the CNC machines. We've all seen this where you have factories where the temperature goes up and down wildly over a period, and my machine is losing accuracy over the course of the day because the temperature is getting warmer and colder. So we wanted to put some evidence behind that to see, well, how much variation is this temperature causing to the machine controller. So we've got some very simple sensors. I think we're called radionics. We stood 3 at the CNC machine, 1 on the casting, 1 on the panel at the front of the machine, and 1 at the back of the machine. And then we stuck a temperature sensor outside, and we could see from nighttime to daytime. What we also did then was we stuck a second sensor on the door, and a large roller door was opening and closing. And we graphed that, and everywhere you see a line here, a vertical line here, this is when the door was open and when the door was closed. So you can see the middle section here was over a weekend where the temperature outside dropped and increased over a weekend. And then on the Monday, you can see where the door on the right-hand side opens and closes randomly throughout the day. But you can see on the right-hand side, you can see the temperatures not consistently changing like it was over the weekend. You're getting more erratic changes. So now we have an image of the temperature within the factory changing related to the door. And then we got controller data, and we started to analyze how much of the positional accuracy of the machine was getting influenced. And we overlaid the 3 data sets. And we can see a clear image here of how the temperature at the machine tool and the environment is influencing or affecting the positional machine position. Now that became important then, because the question here as well, it's if I want to control the temperature within my factory, to what level do we need to control it? You can't make it 21 degrees plus or minus 1 degrees the whole building. That's very, very expensive to do. But if I control it to within plus or minus 2 or 3 or 4 degrees, that might be attainable to do, but how much does that influence the accuracy of the machine then? So there's some of the insights, or how we visualize some of the data that we acquired from some of the different machine controllers on different sites. And these are all done using readily available sensors that we picked up in different areas. Like I said, radionics, I think, is where we got the temperature sensors, the machine positional accuracy, or the machine positional data. That was taken from the machine controller and just visualized in graph with other sensors. And I'm going to hand you over to Paul Moisy now from Dawnlough, who's going to give you some feedback on how the company worked with this project. Thank you very much.
Thank you very much, Chris. I'd just like to take this opportunity to say thank you to IMR for hosting this event and allowing Dawnlough to go through some of our learnings and our experience in the process, and also to thank everybody for joining today. So I suppose I'll go through Dawnlough's experience in the same format as Chris did. So I'll start off with the DDMS project that we did with them. So that project was kind of started off initially looking at preventive maintenance solutions for our CNC machines in-house. So as Chris was saying, we used a vibrations monitoring system for the spindle. The machine that we put that monitoring system onto, we actually cherry-picked that machine because we had noticed anomalies in that machine prior to the experiment. So some of our programmers and tool makers were sometimes struggling to maintain accuracy and tolerances. So we monitored that machine, and we could see that there was a vibration signature, and we were checking it before and after with the warm-up cycle check that Chris previously explained. But a number of months into the experiment, we decided that we were actually going to swap out the spindle on that machine. Now, as Chris explained, that was an expensive process. About a week to a week and a half of downtime for that machine, if you're lucky, if there's no complications. But we swapped out the spindle anyways, and immediately we could see an improvement in the quality of the parts coming off that machine, the surface finishes, and the tolerance capability of that machine. But interestingly, we were able to see real time, or before and after the spindle change, what the old spindle looked like in regards to vibration, and then what the new spindle looked like, and the difference was phenomenal. There was a clear improvement in a reduction in the amount of vibration that the spindle was putting out. So what we were then left for, what we still have now running at the moment, is a real-time vibration output of that spindle. So we can now see over time how that vibration is trending, and then our facilities team can then put in preventive maintenance actions, order a spindle in advance if they feel that it's coming towards the same kind of area as the previous one did. So it's a really, really interesting outcome regarding preventive maintenance. One of the unforeseen gains that we got from this process was the cultural impact of it. So because we were doing this project with some of the guys on the shop floor, some of our tool makers and some of our programmers, we were engaging with them to develop the process and stuff like that. And they were able to look at us collecting data. They were asking questions about how the data was used, how much data we were getting, and the frequency we were getting and stuff. And that made the guys on the shop floor and the team as a whole more aware of big data collection and what can be done with that. In Dawnlough, we use a ERP system to track jobs through the shop floor for on-time delivery and that kind of stuff. And we saw, within just that work center, we saw a 29% increase in operator engagement. So it was a huge gain in data quality for us. It means that we can trust our system a lot more because the guys are informed about what big data means. And not only that, but because, like Chris was shown previously, we had the efficiency of the machine displayed in real time on the wall beside that machine, and that efficiency was taken directly from the machine PLC. And because the operators could see this information in front of them, we actually saw a 24% increase in the efficiency from that work center, which is quite considerable. Like in Dawnlough, we have nearly 100 CNC machines. Probably nearly 50% of the machines have the same type of controller as this particular machine has. But not only that, we actually have 3 machines that are identical to that machine. So if we were to deploy this solution onto those other machines, into that work cell, we would see savings close enough to a 6-figure sum, which is considerable savings for the company as a whole, you know. So to summarize that first project, we gained preventive maintenance insights, but some of the bigger insights that we got were the cultural development, like the ERP system engagement and more awareness of process and efficiency and that kind of stuff. So that's the summarize the first one. Moving on to the CN Connect project with the coolant monitoring system. So coolant usage in Dawnlough is quite considerable. Every machine that uses a cutting tool uses coolant to cool down the carbide or the high-speed steel that we use for cutting materials. And we cut a lot of exotic materials like titanium and Inconel and hardened stainless steels. So the carbide usage within the organization can be quite high. So what we're hoping to gain from this, and what we will gain from better visibility of the coolant state, is we'll gain better cooling properties of the coolant. So the coolant will be able to cool down the carbide more efficiently, and then increase the longevity of the actual cutters themselves. So that'll reduce one of the overheads for Dawnlough. The other benefit is that there will be an automated email system set up. So with our facilities team, if the coolant concentration or the coolant level or the coolant pH goes outside of a desired range, the system can be set so that it emails our facilities team automatically to let them know that the coolant is moving out of its desired range. If the pH moves out of its desired range, what can happen is the coolant can actually have bacterial growth in it. And this means that the machine has to be put down immediately, and it has to be, the coolant tanks have to be emptied completely, washed down, sterilized, and refilled. And you're talking about at least 1, if not 2 days of downtime. So that type of automated preventive maintenance will be really beneficial for the organization. It'll also increase the operator's visibility of coolant and stuff by displaying it on a real-time data screen. And then finally, the final kind of interesting saving for us is the actual monetary saving by power reduction. And as everybody knows at the moment, the cost of power and running big companies like this has increased significantly. So by monitoring the power and identifying that non-value add downtime, we can try and decrease that by either turning the machine off or having operators to cover that non-value add downtime, so then it turns to value add. So they're the savings and some of the benefits for Dawnlough. The outcomes that we didn't see were the cultural, that we didn't expect, sorry, were the cultural benefits of the engagement with IMR. So from my side, that's everything. I think I'm gonna hand back over to Gary for a bit of a Q&A session. Thank you so much.
Thank you, Paul. Yeah, really interesting insights there, especially when you're talking about the numbers and the 6-figure savings that can be made. I'll bring Chris back in now too, and we'll go through some of the questions that have come in. So, Paul, you mentioned that you approached IMR around these projects, but how did Dawnlough know that IMR might be able to help with this?
IMR is supposed to have quite an extensive research facility in Mullingar, and we deal with other manufacturing companies on the West Coast and all around Ireland, and through word of mouth and through some of your social media posts and stuff like that, we could see your capabilities. I mean, IMR have fantastic background in manufacturing and research, so when we wanted to kind of expand our knowledge of Industry 4.0 and data collection and how to get information from our machines, which is a big gain for us. So that's it was through word of mouth and by seeing you guys, the work you guys have been doing.
One question here from Ray. In terms of coolant monitoring, was it temperature and pH that was measured or more?
So in terms of coolant monitoring, we were looking at the level of the coolant in the tank. So we had 2 different coolant level monitoring processes in place, one with mechanical switches and the other one using ultrasonic detection. And then there was the temperature monitoring of the coolant. And so that we can tell whether we can actually trend the temperature during the heat spell, which was really interesting. We could see it moving day by day. And then there was also a particulate count that we were measuring. So we're looking at the amount of small little metal particles in the coolant to see how that affected the coolant or didn't affect the coolant, and the actual the effectiveness of that on the carbide. And then finally, we're now measuring the concentration of the coolant, which is really beneficial to maintaining a consistent tolerancing and machine capabilities.
Very good. And you mentioned a little bit about machine downtime. Was there much of Dawnlough's time taken up during the project, personnel time and machine downtime?
I suppose in regards to machine downtime, there was probably, I'd say in total 5 hours of downtime. So that was spread over two visits from IMR. So the first one was when they actually set up the physical monitoring unit, and the second time when they came on site to set up the software and do all the connectivity and stuff like that. So about 5 hours in total of machine downtime. And then in regards to personnel, between our bi-weekly visit and then liaising and talking with the guys on the shop floor, I'd say you're looking at around an hour and a half a week, just to keep everything up and running.
Very good. And Chris, how are these? We had the question in the poll about funding, but how are these type of projects or this kind of work funded?
They can be funded through different streams. The first one we did, there was a DDMS project. That was a Smart Eureka project that was co-funded with Enterprise Ireland and the Spanish equivalent. You also, there's access to European funding mechanisms for this. There is also Enterprise Ireland funding through an innovation partnership program, which is used for the CN Connect project, where initially we did a feasibility assessment to see if it was two things. One, is it feasible to monitor the aspects the companies want to monitor? And two, is it commercially viable? And will they get the outputs that they want from it? And that then pursued into a project. So when it comes to accessing funding, the real thing I said there is identify the challenge statement or what problem you're looking to address. And then you can always find funding for it, because you can get funding from a €5,000 voucher to a €250,000 research project. It really depends on what you're trying to address or what challenge you're trying to address, and whether it's a 6-month project or a 3-year project. There's lots of different ways of getting funding.
Very good. And where is the sensor data stored? And is there a Power BI expert in-house which created the visualization?
Power BI experts in-house, yes, we do have. We have a data analytics team. Amanda Freeman is the person that worked on the Power BI for us. So she ingested the data and she collated and visualized it in different formats in different ways. And then we also showed the companies how to set Power BI up for themselves so that they can actually use it. So we're sending the data to them and they can play around with it as well and visualize it different ways too, which is very important. With regard to storing of the data, and the data was we've set up an edge device beside the machine that correlated the data and streamed back the data to the level of data that was required, and then that was taken offsite remotely. So we set up a 4G router on each of the 3 sites, and then we took the data off to remotely visualize it and then use the data.
We'll get one more in. This one's from Noel. Is it possible to explain more how the 24% efficiency gain was realized, and in terms of culture, did the operators feel that they were being monitored more, leading to some of the efficiency gains, and is that a risk for attrition?
I suppose I'll take that one. I suppose the 24% efficiency gain, we were looking at the throughput for the cell. So we're looking at the amount of workflow through that particular work center that was captured by our ERP system. So we schedule work for in each individual work center. So we were just able to monitor the increase over the duration of the project so far. And that's where that 24% efficiency gain came from. So it's a gain in throughput and the amount of jobs going through that machine. In regards to the operators and the improvement in operator engagement, there was a little bit of that, probably, that because the number was there, they felt like they had to perform. But we have a fairly robust pit meeting process here in Dawnlough. So we have production meetings every day where we talk to the team about their issues and problems. And maybe for the first week and a half, this question came up with them, and they're kind of questioning like, oh, what's it going to be used for? And we made it very clear that we're not really interested in looking at the operator's efficiency as such. We know that our guys work well and they're all very experienced. We're more interested in the performance of the work center. And if there's an issue, something's not working well, we go to them and we say, okay, well, what's the issue? Is there something that we can do to help you? Is there something that we can do to a process we can put in place to improve the system? So I don't think it affected attrition or anything like that. I think it actually improved communication between top level and shop floor personnel.
Very good. Thanks for that. So thanks for your questions, and thank you very much again to Paul and Chris. We'll be back again with another webinar soon, so keep your eye out on our social media and on our emails for that. And yeah, and as well for the manufacturing event, the precision engineering event that we're going to have in September. So thanks again for joining, and have a great weekend.